Hi, good afternoon, good evening. I was wondering how many people would hang around for the last session, so I see there's more than expected, so I appreciate that, thank you. I won't keep you too long from your Guinness and your snacks or your commute home. So today we're going to talk about feature hashing for scalable machine learning. First, a little bit about me. Jules mentioned I'm a principal engineer at IBM Spark Technology Center working on machine learning and Apache Spark, a committer and PMC member of the Spark project, and I've written a book, Machine Learning with Spark. You can find me at MLNick on Twitter, GitHub, LinkedIn, and so on. So the agenda for today, we'll start with a gentle introduction to feature hashing. What is it, and why would you want to use it? And talk about how feature hashing is used in Spark, initially HashingTF Transformer, and the new FeatureHasher Transformer in Spark ML. And then look at some experiments about performance of the feature hashing, and talk about future work and directions. So most, if not all, machine learning models work on numeric vectors. But most, if not all, features are not actually numeric. So some of them are, but a lot of the interesting features that we want to work with are categorical. They don't come in a neatly packaged numerical vector format. So, for example, tags and other kind of metadata, geolocations, times of day, search terms, text. These all have to be encoded from their raw form into feature vector, into some numerical form. And even numerical features, continuous features, are often more useful when binned into some categorical feature. So a couple of popular encoding schemes for categorical features and text. For categorical features, we have one-hot encoding, which effectively transforms every individual feature value into a vector where all the entries are 0, except for the entry that is of interest for that particular feature value. And bag of words is an analogous encoding for text. So it looks very similar, but each entry in the vector represents one term or word, and the value is typically a token count, so the counter of the number of words in that document. Now today we're going to be talking about sparse data. So many domains have very high feature dimension, but the data is dense. So think about images, video, your kind of popular deep learning type of use cases. Those are very high dimensional input data, but they are dense data. We're concerned here with sparse data. So the types of domains like recommendation engines, e-commerce, online advertising, social networks, video sharing sites, text and natural language processing. Typically, you have many different features, and some of them have extremely high cardinality. So for example, we might be looking at user IDs in an e-commerce site or an online advertising setting. The number of distinct users that we can have can be hundreds of millions, if not billions. So the model sizes, even if we're training simple linear regression, logistic regression, can be extremely large. And likewise, if we want to scale up to more complex models like factorization machines, or perhaps even a deep learning neural network, those model sizes can explode very rapidly. So we may want to try to use some dimensionality reduction techniques here. We could be talking hundreds of millions or billions in terms of feature dimension. We want to compress that down significantly. So something that works for sparse data is known as the hashing trick. And the way this works is that we will map these feature values into a hashed feature vector. And the trick really is that that hashed feature vector has a dimension that is substantially smaller than the original input dimension. So, for example, if we're looking at a categorical feature where the city is Dublin, the first step is we apply a hash function to city equals Dublin, just as a string, for example. And that'll give us a hashed value, which we then effectively divide by the size of the hashed feature vector to get the index of that feature. And we'll use a indicator value of 1, which effectively gives us one-hot encoding. but compresses the vector size down substantially. So similarly for continuous features, we can do the same thing, except this time we don't hash a feature name equals value string, but we do the feature name. So we use the hash of, for example, stock price, again get the hashed value and modulo that into the feature vector size to get the location in that smaller vector where that value sits. So why would we want to do this? Well, the main benefit is that we can compress a very large feature domain down into a very small one. It's very fast and simple. It preserves sparsity. So many dimensionality reduction techniques end up with dense data that don't preserve the sparsity pattern. Feature hashing does. It's very memory efficient because, of course, we limit the feature vector size, but we also don't store the mapping from feature name to index in the smaller vector. So that's something where your typical one-hot encoding requires you to store that, and that's where a lot of the pain comes from, because for very large feature domains you have to store that mapping, which is itself takes up a lot of space. It works really well for online learning. It can easily handle missing data, and you can perform some interesting feature engineering on the fly. So as you're hashing these features into the vector, you can, for example, perform feature crossing and interactions on the fly very efficiently. So of course there's no free lunch or no free Guinness, I guess, and there's these benefits come at a cost. And the two main ones here are, because you're not storing that mapping from feature value to index or feature name to index, you have no way of going back. So whereas if you encode strings and do one-hot encoding, you can always go back to figure out what your features actually are, and do things like feature importance and interpretability. You lose that with hashing. So that is an issue. And then the second one is hash collisions. So of course we're using a hash function, and we are then mapping that down into a lower dimension. So inevitably, we're going to get some collisions where, two different features will hash at the end into the same feature index, and they will offset each other. So that can have an impact on accuracy. And one way of addressing that is to use a signed hash function. So one feature might hash to a positive value. Another feature that happens to collide with that feature may hash to a negative value. And the idea is that in aggregate, the mean value is kind of zero and it's unbiased. So that's one way of alleviating that. But it turns out that the impact on accuracy is actually very low for sparse data, as long as you use a sufficiently large hashed vector size. Okay, so feature hashing has been made fairly popular in certain libraries like scikit-learn and in Vowpal Wabbit, for example. And until recently, the only way that you could use hashing in Spark itself was with the HashingTF Transformer. So this is a transformer that effectively acts as a count vectorizer. It turns a document, basically a set of text, into a bag of words vector, similarly to what we saw before. But instead of computing a full vocabulary and doing an exact mapping with an explicit feature to index mapping, it uses the hashing trick that we've just discussed to compute the feature indices and reduce the dimensioner. So this is kind of how it looks. You can use it in a pipeline, and typically, you take raw text, you tokenize it into a set of words, you pass that through the HashingTF, and you get this sparse vector here. So by default, it's 2 to the 18 is the power of is the size of the output vector, and you can see that effectively we've got term counts there, and because we've used hashing. These feature indices are not kind of linearly increasing, they're all over the place. But we have preserved the sparsity. Now, it's great that you can use feature hashing for text documents and sequences of strings, but we would really like to use it for categorical and real features. So up until now, we couldn't really do that out the box. But we can use what I have come to term the stringify hack. Which is basically, converts a data set that we have here, which has a bunch of, let's say, categorical columns, and we want to convert that into a sequence of strings that can be used as is in the HashingTF. So to do that, we basically extract the column name equals value. So we turn, I1 equals 1 into this first element there, and so on. And then we can just use HashingTF exactly as we have done before and treat it as a document and create a kind of bag of words. And we end up with one-hot encoding. So that's great. We've solved part of the problem, but clearly this operation here is not, it doesn't fit nicely into a pipeline. We lose all the benefits of using Spark ML pipelines, cross-validation, and so on. So we'd like something a little bit better than that. So I've worked on a FeatureHasher, which is inspired by scikit-learn's FeatureHasher and does pretty much the same thing. So it's a flexible, scalable feature encoder that uses the same hashing trick that HashingTF does under the hood, but it can support different kinds of columns. So you can support real numeric columns, as well as string or Boolean columns for categorical features. And unlike a lot of the feature encoders that live in Spark at the moment, in particular string indexing followed by one-hot encoding, which is the typical approach for categorical features, this is a one-shot feature encoder, so it can operate on multiple columns at a time and effectively coalesce them all into one feature vector. So it's both encoding and vectorization in one shot and in one pass. So the way it works, the underlying technique is very similar to HashingTF, and it's not, it's pretty simple. So we can see that it operates on one entire row at a time using a UDF over a row object, and then it just basically builds a temporary mapping. This is not going to be stored because for the hashing we don't need that, but effectively building a mapping from the feature index to the feature value, and we operate on all the input columns. And we can just, we can just pass in the input columns as a struct into our UDF, and that will appear as a row when the UDF is executed. So the way that the feature indices and values are determined is exactly as we saw before in the intro section. So for numeric features, we just use the hash function of the column name to get the raw hash value, and the value is the actual feature value itself. And for categorical features, whether they're Boolean or string, we use the field name, which is the column name, equal to the value. So city equals Dublin, for example, and we use an indicator value of 1. So we're effectively doing one-hot encoding for categorical features. And then the last step is to modulo that raw index into the vector size. So obviously we want it to be non-negative because we can't have negative indices in our vector. And then we change the value in that map, the temporary map that we're building up, by 1 if it's 0 to 1 effectively if it's a categorical variable, or the value if it's real. So you may notice here that at the moment any hash collisions are additive. So, I mentioned before that you can use the sign of the hash vector. We're not doing that now, so it means that, hash collisions may impact, adversely, but as we'll see, it tends not to actually affect you too much. And then finally, we just, create our sparse vector using that index to value mapping. And we're done. So we can take a data frame with a bunch of columns. Some of them are going to be categorical, some of them are going to be real, and we transform it into a mixed vector, so where the categorical features are effectively one-hot encoded, and the real numeric features have been hashed into that vector, but the value is the actual feature value. So that's it's a one-pass encoder. We only have to use one feature transformer. We don't have to put together a whole bunch of string indexes, one-hot encoders, vector assemblers, and so on. But what does it actually work, and what is the impact on accuracy, on performance? So first of all, we'll look at HashingTF for text classification. So this is a fairly small example data set for email spam on Kaggle. I think the total vocabulary size is around 50 or 60,000, So it's not huge dimension. But really we can see here that the baseline will be a count vectorizer operation, which does an exact bag of words mapping, and the HashingTF actually slightly outperforms it at low hash bits, which at first looks a bit odd, because lower hash bits should result in a smaller vector and more hash collisions. So why is that happening? So I thought, well, perhaps this lower vector size is having some sort of regularization impact. So if we apply some regularization to the actual model, this is just logistic regression, then we actually see that hashing slightly underperforms, but of course, the scale here is so tiny in AUC, it's not really that significant. And that kind of looks roughly more in line with what we would expect. Okay, so on to the FeatureHasher and slightly kind of bigger, more interesting data sets. So ad-click prediction is one of the use cases that I mentioned earlier. It tends to fit, it tends to be a perfect fit for feature hashing. The type of data that we're talking about is huge, very high dimensionality, typically a few features which have extremely high cardinality, so many different values, but extremely sparse. So you can see these are some common ad-click prediction data sets on Kaggle and released by Criteo. They've got a display advertising challenge data set with 45 million examples, 34 million feature dimension. The larger version of that is, I actually only used the 7-day subset, but I think there are 21 days in total, 4 billion rows and I think close to 800 million feature dimension. So this subset is 1.5 billion rows and 300 million feature dimension. But all of them are extremely, extremely sparse. Yes, and we can see that relatively small numbers of the features make up almost all of that feature cardinality. So these, we don't actually know what, because the dataset doesn't tell us what these features mean. But we can surmise, given that it's an online advertising dataset, that these are probably things like user IDs, product IDs, maybe some sort of search keywords or kind of metadata, geolocation, things like that, that tends to have very high cardinality in these domains. And we can see that a few of the features occur in almost every example, but it very rapidly tails off. So some features you only see very seldom. So this looks like a good candidate for using something like feature hashing. Now the challenges that I ran into in even trying to do these experiments with Spark ML and compare to the baselines are probably similar to some of the challenges that you might run into. So this is what a typical pipeline looks like if you're doing exact mapping. So you start with a bunch of columns for mixed categorical and real data, and you want to one-hot encode your categorical features. So for each column you create a string indexer, you create a one-hot encoder, and then at the end you assemble that together, and that should work perfectly well, right? Because we're talking about 34 million dimensionality vector. It's not that big, so it should work. But it doesn't. Even on a very large cluster, I consistently ran into issues, and some of you might have also run into similar issues. Won't go into too much detail now, but if you dig into that, a lot of these issues come from the fact that Spark ML is trying to store some metadata as we go through this data frame about each column, and it's actually storing the kind of feature names and effectively storing that feature mapping in a way that is not so efficient and sadly can't be turned off at this point. So what you end up with is that you can't even complete these pipelines. But we can apply the feature hasher and we can deal with that pretty easily. So this compares on the Criteo display advertising smaller data set and the Outbrain news advertising, news article recommendation data set, compares the AUC for different hash bits. So Criteo is basically just take the data set as is and apply the feature transformer. Outbrain the data set's a bit more complex. It has a few tables. Just took a very simple bunch of the column, joined it together, took a simple bunch of the columns and mapped those through the feature hasher. So we can see that, number one, we can actually run this and it doesn't blow up. It's very fast and efficient. And we can kind of see that the performance doesn't change a lot as we change the hash bits. Generally speaking, we would kind of expect that lower hash bits would be performing a little bit more poorly because of hash collisions, which is kind of on the left what we see. The outbrain one is a little bit odd, but again, if we look at the actual scale of these axes, really there's very little difference here, and that could be accounted for by a bunch of random initialization or whatever the case may be. So as I mentioned, there's a subset of the Criteo 1 terabyte dataset that I used. And you basically cannot train this out the box with Spark ML. First of all, you run into these vector assembler issues and one-hot encoder issues. And second of all, you have this 2 gigabyte broadcast limit, which effectively means you can't even, even if you could get those feature extraction transformers to work, you're going to fail there. But we can reduce this 300 million dimensionality data set down to 16 million hashed features, and we can train it successfully. Okay, so in summary, feature hashing is a fast, efficient, flexible tool for encoding both real and categorical features. It allows you to scale up to extremely high-dimensional sparse data without giving up much, if any, accuracy. Of course, that doesn't apply to all data sets, and definitely only use it with sparse data. It doesn't help you with dense data. It supports multi-column one-shot encoding and vectorization, and it avoids these common issues with Spark pipelines, such as string, components such as string indexer, one-hot encoder, vector assembler at scale. I should note that these issues are currently being worked on. So, for example, one-hot encoder is being improved. String indexer will have multiple column support going forward, and there's talk about improving this ML metadata and the scalability issues with vector assembler. But for now, they don't allow you to scale to this kind of data. So the good news is that this started out as a little bit of a research project and an idea, and it's now part of Spark ML Master. It'll be released for 2.3.0, which will be hopefully around Q4 this year, maybe early next year. There's the JIRA if you want to go and look at the details. So it's not complete in the sense that it's complete in that it works, but there are some improvements that can be made. So as I mentioned, signed hash functions is one of them. We can try and avoid the impact or reduce the impact of hash collisions using signed hash functions. Currently, numerical columns are always treated as numerical, and there's no way to treat them as categorical. So one has to, actually, it's a bit of a pain at the moment. One has to then cast those to strings in order for them to be treated as categorical. So a fairly simple fix will just be to allow the user to specify the set of numerical columns that will be treated as categorical. So if anyone wants a good starter pull request for Spark ML, that would be a great one to work on, and I would be happy to shepherd that through for you. And then something a little bit more complex, but also very interesting, is this idea of internal feature crossing and namespaces. So Vowpal Wabbit, some of you may know it, a very popular online learning, machine learning library. Doesn't only do online learning, but that was its kind of focus, very fast. And it really popularized this feature hashing concept. And what they do is they do on-the-fly interactions and crossing of features. So rather than exploding this vector using a polynomial feature expansion or something like that, which exists in Spark ML, but rather than doing that explicitly and exploding your memory, they do this on the fly while computing the hash functions. And that I think would be something that would be great for this feature hasher. And then finally, I've given a version of this talk earlier in the year, and this was actually an idea at that point, and someone in the community has since gone and independently of my talk, maybe inspired by it, I don't know, has gone and actually created a pull request for this. But scikit-learn has something called a dict vectorizer, dictionary vectorizer, which is very similar to the feature hasher, but it actually does the exact encoding, the exact mapping. But it can work on multiple columns at a time, and it's a little, it can make the reverse mapping a little bit more efficient and a little bit easier to use. So the reverse mapping of, of your feature vector back into what the feature names are. So that's something that is still a work in progress and still an outstanding PR that I need to do some review on. Okay, so there's a couple of references, academic papers, and the two libraries I mentioned that have implemented this for a little while. And I look forward to FeatureHasher being in Spark in the next release, and for you to all use it to scale up your sparse machine learning problems. Thank you.
Thank you, Nick, for sharing that contribution to HashingTF, which will be in Spark 2.3. Hopefully, it will be at the end of this December or early next year. Any questions for Nick? We have 2 mics at the end. Yeah, go ahead.
Oh. Hi. Since no one asked a question, then I ask the question. But it's not about feature hashing, so some quite close to it. The countervisor. Shit, I forgot the name.
The count vectorizer?
Oh, yeah, yes.
Okay.
When we use it, we find out that if some string is not in the training set, then it will, the vector it generated doesn't contain that string. So so in some using scenario, we need to doing the normalization based on the length of the string. But since that one is missing, so it brings some awkward situations. We need to hack the ML class to do some customized normalization. So I'm wondering what's the design philosophy behind it. So if a string not in the training set, then this counter vectorizer doesn't put it into account into the vector.
Okay. Yeah. So the count vectorizer itself will obviously, and then off the top of my head, if I recall, for anything that is not in the vocabulary, it'll basically return an empty vector, empty sparse vector. So I mean, there are obviously many ways of dealing with missing data. You can, you can either kind of ignore it like that, or treat it as completely missing or an empty vector. Or you can try and create a kind of special word or kind of mapping for unknown data. So that's something, for example, in the string indexing in Spark, you can do that. You can either kind of throw an error and say, hey, I don't know what to do, blow up, or you can kind of ignore it and treat it as kind of empty, or you can create a special bucket for that stuff. So count vectorizer, I kind of believe that just ignoring it or treating it as empty vector is probably the more principled way of doing it. For normalization, I guess are you talking about TF-IDF or BM25 or something like that? It could be that that use case then of adjusting that normalization factor based on the length of the document or something like that, that's missing from Spark. So that could be an interesting kind of thing to add to I guess it would be to the IDF element, or perhaps as a parameter for the term frequency to adjust some form of normalization. But yeah, it doesn't do it at the moment.
Well, thank you all for coming. Give a big hand to Nick for the wonderful contribution to 2.3.
Thank you.
I want to wish you all a safe journey back home. Thanks a lot for coming to Spark Summit. Remember, we'll be back next year in London. And if you wish to come to San Francisco for the CFP full call for papers will be opening in about the first week of November. So keep your eyes open. Thanks a lot for coming. I hope you had a good time. And take your Spark moments in your memory and share it with others. So thanks.